That kind of works.
Okay.
It's only funny because we were told that this works perfectly and we don't have to worry about anything, so obviously Marfi is with us. So, again, welcome to our talk called Gentle Introduction to Log-Free Programming. If you are surprised to see us here with this talk, I have to say we were as well, because yes, it was a last-minute change, but we're very happy to do it. You're in for a treat. This is the international premiere. This is a very new talk. So we would love to hear all the feedback that you might want to give us. And because we're going to talk about log-free, and we love dry jokes, those are exactly not the logs that we're going to talk about. So I think we all know that it's 30th anniversary, 30th birthday of Java. We're very happy users of this platform. And let's start with about us.
About us, okay. So, hello everyone, I'm Jarek, and I work at Neo4j. Anybody heard about Neo4j? Yes, that makes me happy. So, if you haven't heard, we are doing the graph database, native graph database, and I work there for like 7 years as a team lead for the database benchmarking team. So, I try to make this think fast and break stuff. Apart from it, I'm with JVN since 98, probably, 99, version 1.2. And yeah, I speak a lot of conferences, but actually this is my first presentation in Portugal, so just be gentle, okay? And I have a weird sense of humor, so I don't know how it will work. And here's
my name is Andrzej Grzesik, and I'm building a startup called DataLinks, which is trying to bring context into AI, which is a lot of very interesting things. Specifically, we are not a database, he is a database, and we might be using what he's producing. I'm on Twitter, I have an email, so if you want the slides, we're happy to share, just drop us an email. I also identify with those images. I would mention Polish Java User Group, Java Champions, Geek on the conference, but that's that. And we love dry jokes. And dry jokes are there for us to remind that at least I have to drink something. So.
I'm sorry.
Yes, what is log-free?
Important question. How many of you know what is log-free?
I see 4 hands, 5, 6, maybe 8.
It's decent. Okay. So if you know, it can be boring. If you don't know, it can be mind-blogging and destroying, and you will feel like your brain will fry at some point of time. So we'll start gentle. What is log-free, Andrzej?
Well, before we get into log-free, we have to say what are the basic building blocks that we want to use so that we can talk about what log-free is. And the most important one is something called progress guarantee. So a guarantee that the software or the system as a whole is making progress. Something has happened, and then something else has happened, and whatever progress might mean. Okay, so, progress guarantees.
So what are the progress guarantees? So imagine we have a multi-threaded program. Probably your majority of us work with concurrent systems. So the progress guarantee says something like this. But there is a way that we can ensure that our program, even if it's running from multiple threads or processes, will make progress. Not necessarily do the stuff you like to do it. It can do some weird stuff, but it will make progress. At the end, your task will be completed in a multi-threaded environment.
And because of that, there is a different way to approach it. There are different levels of progress guarantees, liveness levels. The first one is called obstruction-free. That means one thread working in isolation in a system will not deadlock itself, and it will complete.
Yeah,
it's
so
very simple, but this is the lowest thing.
And one thread at a time will do the work. Then we have log-freedom, which is like a more relaxed thing, but it says not necessarily the one thread will make progress, but system as a whole will make progress. So this is the difference between obstruction freedom and lock freedom. In obstruction freedom, one thread makes a progress, and in lock freedom, the system as a whole, so set of threads, will make progress. It may happen that some threads will not get enough time and will starve, but the system as a whole will make progress. And then we have the strongest progress guarantee, which is wait freedom.
Which is amazing, because that's, if we're operating under those assumptions, every single thread in the system will complete whatever we wanted it to do in a finite number of steps. Number of steps can be big, but it's finite.
So we know upfront how many steps is necessary. In wait freedom, how many steps is necessary to complete the task.
And before you switch the slides, I'll just point out that lock-free does not say anything about locks in here, and we'll explore that concept further, but it's important to already note.
The name is, as always, in computer science, misleading, you know. Naming things is hard, because it's not about not using locks. So this is a really nice quote from, I really recommend this blog. It's pretty old, but things didn't change since late 20s. So it says lock freedom, it's basically the program will be able to complete in some number of steps, and if you give the program infinite number of steps, infinite time, it will complete. Eventually, it will complete. So it's basically, there is no lockups. There is no possibility to the program to block. So it's not about locking, it's about non-blocking. I think non-blocking would be a better name.
I really like the concept of give me multiple infinities of steps and then I will be able to do everything.
Yeah.
So, a single construct in your favorite language, can be any language you like. Is this code thread safe? Who thinks this is thread safe? Wave.
Okay.
Who's sleeping? Good. Obviously, we're putting it out there for a reason, which means there's probably something wrong, which means that is not really thread safe.
Because what you saw is a single, you think it's a single instruction, yeah? It's I++. But if you look at the lower level implementation, it's actually 3 instructions, at least 3 instructions. It depends on the CPU architecture and all these nasty details. Because first you need to fetch the value, so that's 1. Then you need to increase the value at second instruction, and then you need to store the result back. So this simple I++ is actually 3 instructions, and threads can interleave, and any threads can interrupt the other one and fetch the value, the wrong value, and increase the wrong value, or even overwrite the value written by the first thread.
So if the number of threads that you're running with is 1, everybody's happy, but if you have more than 1, it gets tricky. So in order to have something useful, there is a concept of atomics, or atomic operations. Why are they so cool?
So I think the best explanation is think about a database transactions. So atomic operations are like begin, do modifications, and commit. So the atomic operations usually come in the form of read, modify, write. So you read something, you modify it, and write the value back. And it is seen as a single operation. It's still 3 or 4 operations, or even more. But from the CPU level, I mean even from the programmer level, programming the CPU, it is seen as single instruction. So there is no way that one thread will fetch the value, the other one will increase it, and then you will fetch the old value and overwrite. Because it will all happen in single instruction. It looks like single instruction, it is not. How it's implemented? Of course, it is implemented at the hardware level. So CPUs these days support atomic operations, and it's a pretty old concept.
So we spoke about lock-free, and then this still mentions locks on the hardware level. So you cannot get around not having locks. You have to have them somewhere. What this does is pushes it to the lowest possible level. suited to the CPUs, which means it's great because if it's in hardware, it should be fast.
I think this is the best explanation I've read on Stack Overflow. Yeah, we should probably say bye-bye to Stack Overflow, I've heard recently. But the best explanation I read is the atomic operation is the lowest possible granular block. So how it's implemented? Basically, if you have multiple CPUs, they are connected with a bus, and the CPUs are sending each other messages. Basically, current CPUs are distributed systems. Like system on a chip, distributed system on a chip. What happens is, basically, before you do the atomic operation, you send the message, lock the bus, and don't allow any other CPU to modify and read this value.
Which is cool if you don't have too many cores trying to do the same. If you have many, because you, I don't know, have a very fancy EPIC or Threadripper machine with, let's say, 96 physical cores, 192 threads running at the same time, this can speak of contention.
Yeah. So how it was fixed some time ago, it doesn't require any more locking the whole bus, because it means if you lock the bus, the processors cannot communicate with each other, and it stalls the whole system stops, even if two CPUs, two threads are involved. So now it's implemented using a part of the MESI protocol, and it's a lock on the cache line.
So, MESI, exactly not this one.
Not this MESI, okay? So what MESI is? MESI stands for modified,
exclusive, shared
and invalid. So this is a protocol inside CPU that allows to agree between the cores which value they see from the memory, okay? And whenever we do atomic operation, the cache line, so the part of memory where your variable is stored, goes into exclusive mode. It means only I have this value as a CPU, and no one can fetch it and modify it until I release the exclusive mode.
Yeah, it's state machines all the way down.
Yeah. But it's a simpler version of the MESI protocol.
So, what are the atomic operations that are actually used in software? There are three basic primitives that we're going to show. The first one is exchange. The point is, we want to exchange two values so that nothing gets in between. In pseudocode, this is what it looks like. This is the outside effect that everybody observes, but the important bit, if it's atomic, it happens, well, atomically.
Yeah. So if it's atomic, it means all these three instructions are seen as one, okay? No thread going here or going here. Another way is compare and increment.
Exchange and add, compare and increment, there are different names depending on which language, which pieces of literature you read. The point is, you replace a value, well, you add something to a value only if the value that you would add to matches what you want.
I think you went the slide up front. This is compare exchange.
Yeah, but I wanted to increment, but yeah.
So this is like the most interesting from you will see soon with the examples in Java, but this is the most interesting part of the atomic operations, is you compare values, and if it's equal to the old one, you replace with the new value.
What does it look in Java? Well, in Java you have atomic variables in Java util concurrent atomic package, and they delegate to C, which delegates to assembly.
Yeah, so, you know, we are pretty old, so we enjoy showing C++ code. This is our favorite play. So basically, if you look at JDK code, the OpenJDK, this is from 21 on 23.
This is 21.
21. So what you will see is the compare exchange operator in atomic will be replaced by this lovely piece of generated assembly code. So whenever you do get an increment or compare exchange on atomic variables, the JVM will produce assembly code depending on the platform. So ARM will have different instructions, and PowerPC will have different instructions.
And there is a volatile here, and that volatile here is the C volatile or C++
Yeah,
volatile.
this is the C volatile.
It's not the Java volatile, it's different. I think that's enough.
Yeah, yeah. And as you can see, just to confirm, any atomic operation requires the log prefix. So first you send log, and you log the bus, or log the cache line, and then you execute the operation.
Why should you care? You should ask, why are we even talking about it? Why do we get excited about it? Because apart from doing Java, C++, and assembly already in the first 20 minutes of the presentation, why is that important? So imagine a simple benchmark. We're not showing the code because I think you can everybody here can imagine adding values to a counter from multiple threads. But if you try to do it from multiple threads, interesting things can happen depending on how you do it.
Yeah, because in Java, we can do it, like adding things in a thread-safe way, in a couple of ways. So this is the atomic integer implementation. This is what is interesting, but probably my computer was broken. This is without atomic, so this is not thread-safe version. And then we do the same, so incrementing in a thread-safe manner using read-write log, and then we're using synchronize. If you looked at the numbers, if 58 millions 100 millions operations per second. Higher is better. So this is throughput. So atomic beats the read-write log and synchronized like a couple of times. Yeah? So it's, in this really basic scenario, you already can see that it's faster.
And before you go there, shameless plug for Jarek, there is a long workshop tomorrow about synchronized and log support in Java tomorrow morning.
Yeah, tomorrow morning.
If you want to know extreme details about synchronized, that's then.
Because I like pictures and numbers don't tell the story. This is the atomic performance versus synchronized and read-write log.
As usual, bigger is better.
Yeah, bigger is better. So this is kind of proof why log-free programming can be interesting for you. But how it works, how you do it?
Well, you can try it once, but then you fail and, well, you go sad because nothing happens. But if we want some effect to actually have happened, then the only option that we get if we fail is to retry, which creates a very common construct in programming called a concurrent swap loop, or a CAS loop, or whatever you want to call it. You try until you've succeeded. Because if you try, you read the value, you do your changes, and then you try to do a compare and set. And if in the meantime, somebody else, maybe Jarek replaced the slides because, well, he wanted to do something to me, I see that the slides don't match what I want, then hey, it means the state I operated based upon is wrong, which means I should read it from scratch again, apply my changes again, and try to commit it.
So the essence of this whole log-free programming is this single line, yeah? Compare and set. So what we do, we fetch the state, we replace with the new, and try to install new state with a single compare and swap. And it fails, we retry. So it's kind of like optimistic locking in databases. You can think about it like this. Yeah, so this is like the core of the problem. It's always a loop with compare and set somewhere.
So what are we going to look at? So there are different algorithms or different actual implementations that we could try to digest and cut into, but we picked something very simple. We picked a queue because everybody knows what a queue is. Everybody knows what a queue looks like, how it works. Also, it's simple in its behavior. And if you understand how to work with a queue, you can build more complex things. The reciprocal is not necessarily true.
And what is interesting, this queue, like the basic algorithm, this is Michael Scott queue, is also used in Java util concurrent queues, because this same concept was also implemented in JDK, but we'll show you the simpler version we did. So how it works?
Well, we'll have a couple of diagrams. So first you look at how it works with circles and arrows, and then we'll do the same in the code so that you know what you are looking at in the code. At first we start with a queue with a head that points to a dummy node and the tail that points to a real node, which means the queue has two nodes. We're happy. I think everybody's still okay.
Yeah, so this is the beginning of our queue and this is the end of our queue.
What happens then?
What happens later?
Well, we want to add a node. So we create this new node, right? At first, it's completely unattached to anything. We will have to put it in there somehow.
So we want to put it here, yeah?
Yeah.
At the tail.
Yes.
So what happens? There are two operations. One operation is you need to connect your new node with the tail. And of course, so two operations, connect node with the tail and connect the node with the last node, because this is FIFO-Q. So what we do, we try to install the new node as a field called next on the node, and if somebody, and it's, the starting value is null, so if any thread didn't change the value to something else than null, we are okay to install new node. If it fails, it means somebody put in between this node, so we need to restart.
And let's assume this worked. What you can already maybe see here is, but tail is still pointing at node 2, but we have node 3 in there, which means depending on which side you look from, you might get different results. That's
so we got kind of inconsistent queue.
Yes.
Yeah? So what happens next, we need to point tail to the new node. So this is the second step. We again use cas. And this time, we do cas saying, okay, tail, you no longer point to the node 2, but now you point to the new node. And of course, we do cas because if somebody in between tries to push, some other threads will try to reattach the tail. We need to check. So if tail is still the expected state, install new node.
Important thing between the lines, those are two cas operations. Single cas is atomic, but two cas operations between each other are not atomic. So there is an opportunity for an inconsistency, which there are workarounds. That's the case.
Yeah, it can happen that we attach the node, but we don't attach the tail. And we call it tail lagging. How we solve it?
Well, first, what does the node look like? It's what you would expect. It has an atomic reference to the next one. It has its own value. I think that's pretty self-explanatory.
Yeah.
So how do you add?
I'm sorry, it's offer. Okay.
I want to offer you a node.
You want to offer me a node. So what I need to do, line 4 and 5, we take the current tail and we get the current last node. So we fetch the state of the word. This is the current tail, and this is the current node. Remember, other threads can do the same at the same time. And then we say, okay, we check if the fail points to the next, which means it's still connected. If it's not connected, it means we are lagging. So we are pointing at the wrong tail. What happens? The offer helps the other threads to reconnect the tail. Okay? So this is kind of like one thread which tries to put the node on the queue, will help other threads pointing to the right tail.
Yeah.
If everything is fine, if we have the right tail, we then try to compare and swap the new node, and of course, compare and swap the current tail.
And the whole thing is in a while loop, because we would like this to succeed eventually, which means it is possible if there is many threads, some of them will repeat this piece of work over and over and over, and they will be very unsuccessful and unhappy. Hopefully, eventually, everybody will do what they wanted.
Because if we fail here or fail here, we will retry. So we'll fetch the state again, fetch new node, fetch new tail, and see what happens.
It's somewhat non-obvious, or maybe between the lines, there is no counter of how many times we attempted, because the interaction that we want is we want to put a thing into a queue, which means we don't care when it happens, but we want it to happen. And if it takes 1,000 approaches or 1,000,000 approaches, that's equally as good. And then the reading side.
Simpler. Yeah, polling is much simpler because we take the head and we, of course, always check if we are lagging or if we are empty, but we check the current head and we just switch the nodes. We take the next field from the current head, make it a head, and return the value. So it's much, much simpler. Okay.
You're experts in log-free programming. If somebody believes that they've never done any lock-free, but they use Git, they kind of have.
This is like, I think, really good analogy, because you work with Git, and Git is lock-free, because you don't lock files when you check out files. You check out the file, modify the source code, try to push. If somebody does something to the file in the meantime, you need to rebase. And this is the basic lock-free programming loop. So you need to rebase if there is a conflict.
Somebody could say, yeah, prove it. How do we know it actually works?
It's correct, yeah.
Well, we're talking about it, so obviously it does. But if you really need to test it, how do you go about it? There is a very awesome tool called JC-Stress. It's a piece of the JDK, it's part of the JDK repository. I think it's been called experimental for the past 12 years.
Yeah. It's still experimental, but it's used by all the JDK people.
Yeah, programmers are humans. But what does JC-Stress usually look like? You define actors, which are behaviors, and you define results. And
what are the results? So JC-Stress is used to confirm that your code is correct in concurrent scenarios, and it adheres to Java memory model rules and so on. So basically, in this example, what we are testing is one thread will put something on the queue, and two other threads will compete. What are the results expected? One result is you get null and null here because this one was called after this one. You don't have control over the order when things are called. The other thing is what is expected, you get non-null value and a null value here because this was called first, and of course the opposite. And one invalid value is when both get the value. So this is not the queue, okay? And then what JC-Stress does, runs this example multiple hundred millions of times with different JVM settings and flags. This deserves like separate presentation, this tool. And tries to break your code, okay? Trying to see if any of the use cases are breaking. And of course, what's the one property of the queue? The other property you want to have is happens before from the Java memory model. So there is a special concept in JC-Stress called arbiter, and arbiter is called after your test. So we do the test, run your threads, and when all threads are done, then we call arbiter. Why it's useful? Because we put something on the queue, and then we call poll twice, and what is the expected result?
Well, if everybody gets it, then if I'm extracting money from somebody else's account like that, I'm happy. But if it's somebody extracting money from my account like that, I would be a bit uneasy.
So what you expect to satisfy the happens before is you will always get the non-null value here, and here you will always get null because they are from the same thread. They are not competing.
Important thing about JC-Stress, it runs it many times. It does not guarantee that something is correct. It guarantees, or it can prove that no error has happened.
This is not formal verification.
Yes.
This is the experimental verification.
So far I think it looks quite easy. Everybody's excited. We should all be doing that. But sadly, no.
Yeah. So,
also known as the ABA problem.
ABA problem.
So, an ABA problem is when there is a mutation to some value, the mutation back to the old value, and from the outside world, it looks like there was no change.
Deserve explanation, I think, because it's complex.
Yes.
Okay.
Let's look at pictures, or let's look at text and then look at pictures.
So ABA problem is like the problem is in the description, because what can happen with log-free programming, you can go and fetch the state and see the A. And you say, okay, that's fine. Then you modify the state, the same thread modifies the state to B, and the same thread still in last step modifies the back to A. So the other thread will not notice what you did modification. Okay? So you modify, you fetch the state, both see A, then the other one changes to B and back to A, and the other thread still thinks it's A. It's like super hard to explain.
It looks like there is no danger, or if the only value that gets shared and published is A and B, everybody's happy. The problem is if you have dependent state.
Yeah.
If it's not a single integer, it's not a single long, it's not a single something like that, but you actually have an object tree, or maybe a byte buffer that you make very strong assumptions about, and you don't notice that somebody has completely rewritten it, but it looks the same because, I don't know, maybe the total length looks like what I just checked.
So some pictures. Imagine one thread takes and wants to put something after D, and before A, but after D. And it fetches the state. Then comes the other thread and says, oh, I see B, that's okay. That's okay to change. But in the meantime, the other thread changed to B and A back. So we put something somewhere, probably in the wrong state. What are the workarounds? Because the log-free programming is pretty old concept, they came up with, secret people, came up with solutions. One is something called tagged state reference. So basically, you keep your node, but also together with your node, you keep some kind of tag, like a version, incrementing atomically. So every time when you do cast, you not only check the node, but also if it's the same version. Because if somebody did something in between, he updated the version, so the cast is no longer possible. The other solutions?
So you can use intermediate nodes, which means...
You can put fake nodes in between. So you have nodes with values and fake nodes, and you do the operations of the fake nodes because you never remove the fake nodes.
Another approach is to use immutable data structures, which means if you always publish an immutable object tree, nobody can modify it because, hey, it's immutable. But there are problems with immutability. Sometimes it's not really suitable for whatever you're doing. And there is one thing which doesn't apply to Java, but it's still there.
The third reclamation. Happy, we have garbage collector. People implementing log-free structures in unmanaged languages like C++ or C, they still need to care about freeing memory, which makes log-free even harder for them. The GC is helping us a lot. Okay, so one more example.
Yep, it's called pragmatic implementation of non-blocking lists. It should be great, right?
Yeah, this is the most not pragmatic ever. The title of the paper is the pragmatic implementation. I have never ever seen a pragmatic use of this structure, but it has some interesting ways to avoid the ABA problem.
Let's examine.
So Java has something called atomic markable reference. What it does?
Well, it has expected, it has a new reference, and it has something extra. You can see those two booleans, expected mark and new mark. This is like trying to do two cast operations at the same time. But we're in Java, we don't have multi-return, we don't have multi-things, so what can we do? Well, we can put them in a wrapper. Yeah.
So we put them in a wrapper, and we keep both values in the single, and we always create new markable reference.
And if you hear about wrappers, if you think wrappers, you can also think allocation.
Yeah.
Which means
so the markable reference in Java is not for free, because every loop actually will create new instance of the box type. So how it looks in this
very pragmatic, non-pragmatic list. First, a node, something I think that we've seen the difference is that rather than it being an atomic reference, it's an atomic markable reference.
Yeah, and we mark this reference with the false, so it's not deleted.
Then we will have a traversal. First, the outside of the traversal, the beginning looks like all the other cast loops that you've seen before, with the exception of there is this currently marked, which is an array because, hey, we're in Java. And then let's see what happens in this inner loop.
Okay. So what happens is, this is like the heart of this algorithm. It's basically you are finding the node you are trying to replace. So you're traversing the linked list, finding the spot where you want to put or delete your node. So what you do, you traverse the structure, but at the same time, you check if the node you are looking at was not actually deleted by the other thread. Because how deletion happens in Harry's linked list, you don't delete the node, you mark it as true. And then some other thread will delete it when it spots the true value of your mark. This is unusable. Really. But it's interesting because you see, we traverse the list, and if we only replace the value if both this and this hold true. And then, at the end, we say, okay, we found the wrong node, we remove it.
Sometimes this is called as double cas, because yes, we're doing cas on two things, but again, it's impossible to atomically affect multiple things in memory, because that would not be atomic, so we use a wrapper as a workaround.
And you can see here that when we delete something, when we find the node we want to delete, we mark it attempt mark true. And we try to mark, and then we try to delete. You see what will happen? You mark it as true, the other thread will come in, will say, oh, I see it's true, I will delete, and then you will try to delete it again. Because you didn't know the thread before you tried to delete it. Yeah.
Tom, tom, tom.
Java memory model. How it all works with the lovely Java memory model.
Let's start with the simple things. Get is like reading a volatile. Set is like writing a volatile. That part is easy.
So atomics behave like volatile when you get and set.
The easy getting and
the
setting,
part.
yes.
Okay.
The magic happens the moment you have a concurrent set and increment, because if you try to do it with volatiles, it's not going to work, whereas with atomics, it can.
Yeah.
So if you need to do something multi-threaded and you need to increment and be sure that you increment it from a value to a value, use atomics. What do we have there? We have concurrent set, and we have, well, concurrent increment, get an increment, increment, and get all of the variations. They have the memory effects of both reading and writing volatile variables. Yeah. Then we have lazy sets. What is lazy and what is weak?
Yeah, you lazy set things. So it means you don't care about reading the correct value. Yeah? It's like whatever you read, it's fine. It's kind of relaxed operation. And then you have weak concurrent set that does the thing atomically, but doesn't guarantee that other threads will see what you did, because this is the part of the Java memory model specification. Okay.
So we've talked about some of the basic constructs. Cool. It's probably, is it a signal that you should all try to rewrite your algorithms to lock free? Well, not so fast. First of all, the usual answer in computing is it depends. Performance implications really depend on what you're doing. Also, scalability depends on the hardware and depend on the use case.
And the first thing, not every problem can be made lock-free. So it's not like I want you to go to your computers on Monday and rewrite everything to lock-free, because it depends, okay? And sometimes lock-free and atomics are not that fast. And let's talk when and why. So, and you may also be thinking, what is the application of the atomic lock-free algorithms? Graph traversals. If you do a lot of graphs, like me, traversing the graph from multiple threads, it's easier to be done with lock-free. Even in GC, in the GC algorithm, the garbage collection algorithm uses a graph of objects, and when it traverses, it uses a flag, atomic flag, to check if it already traversed the node. Shared counters, this is what we showed you. Spin locks, if you implement spin locks, You will use lock-free programming and lock-free spin locks. And spin locks are sometimes better because synchronize and rand lock requires call to the grumpy operating system. And this is
and the spin lock can keep a CPU busy and will keep the CPU fast and keep the caches hot. And that's sometimes very nice at the cost of electricity. Whether that's your use case, should you always use a spin lock? Probably not. But sometimes it is very useful to know.
Yeah. I think that the biggest difference is, with synchronize and locks, you call operating system, and with atomics, you talk directly to CPU. You skip the operating system. So what are the problems with atomics? Because it's now that's all dandy and nice. So there's nice research from like 15 years back, but I think it's still up to date. But the problem with atomics is that there is something called wasted work. Imagine you have many threads, like hundreds of threads, trying in this while loop, retrying all the time. So you have wasted work. Somebody was talking today during the opening keynote about wasted work. So this is wasted work because you keep trying and applying the same methods and changes to the state until you succeed. So if you have highly contented scenario, you have multiple threads, hundreds of threads and multiple cores, and all of them spin on the atomic cast, it can be a waste of your resources. What is another problem with the atomics?
Well, they prevent instruction-level parallelism, which means they break something that's very dear to our hearts and completely opaque to us as well.
Yeah.
CPUs don't execute the code that you write directly. They do some magic for the sake of this talk. Using atomics prevents it, and they prevent lots of speed-ups. Sometimes it might be because you used an atomic and CPU couldn't apply certain optimizations, code can be much slower. Somebody claims 30 times in simple writes. We haven't run the benchmarks because they all very deeply depend on the hardware and so on and so on. But there is that effect.
Yeah.
If you rely on CPUs optimizing your code and using SIMDs and fancy things, then be careful.
And the things will get even worse with more cores and more caches and more layer of caches, because it means you need to synchronize a lot more CPUs, and which will block the other ones waiting for the one to do the CAS operation.
Summary. Yeah, we already talked about the example, but block-free is very much like working with Git. You check something out, you apply your modifications, and then you try to commit. And if somebody did some updates, then, well, you update yours, and then you retry to commit it. That's the mental framework. That's very convenient for it. Should you use it? Should you write your own? No. There are excellent existing implementations.
Why not?
Okay.
If you have like lonely morning or evening, weekend, lonely evening, your spouse left you, you have beer, what the best time? Just write some log-free. It's like, makes you happy. But yeah, don't write your own. It's really hard to get them right. It's good to understand how they work and be aware of this kind of structures, but use existing implementations because a lot of these structures were already implemented.
If somebody at work tells you that, hey, we should make it log-free because it will be faster, you can say, hold on, let's write a benchmark. And then you spend 2 evenings together having fun, or maybe weeks or months, depends.
Because I was doing benchmark for last 7 years, I know benchmarks lie, and benchmarks are the biggest. I professionally lied to my boss for 7 years. They lie, and you always need to write your own benchmarks and run because it depends on your use case.
Which ones should you use? Which ones can we recommend? This is not a complete list. Agrona is great, Disruptor is great, JC Tools is great. There are even classes in the JDK.
So even in JDK, you have some classes which implement log-free. So concurrent hash map, not in all cases, read the Java docs, because not in all cases it's log-free. In some cases, most of the cases, but still there are some corner.
But if you're using concurrent hash map, you can feel better because, hey, I'm using something log-free.
Yeah. Concurrent link queue, link transfer queue, and a couple of other things that are in the Java util concurrent packages which implement the log-free algorithms. Oh, a wrong slide, I'm sorry. When
you really care about performance, it might be a solution, but you have to benchmark it. When you really want a cool topic to explore because you maybe need something to do in the evening, when you really like figuring out how hardware works, and when I mention hardware, we have to mention hardware really differs. AMD versus Intel versus ARM versus hosted ARM all behave very differently. It's a fascinating exploration, but there is lots of complexity.
But I think the last thing may be the most appealing for you if you care about latency. You know, it's like your problem is not 100 milliseconds, but you do sub-millisecond things. And you really care about low latency. Log-free is one of the options worth to explore. And I was recently reading a nice article that a lot of structures inside of Linux are log-free. For example, the scheduler and other things, like buffers and TCP stack. So it's used a lot in other things as well.
And with that, we're reaching the penultimate slide. This one says thanks, so you can raise your hands and start putting them together and away, repeatedly, in a log-free or log-full fashion. If you have any questions, we'll be around, we'll be here at the party. Jarek is running a workshop tomorrow. If you want the slides, feel free to drop us an email, take a picture of this. We'll be happy to share, but we don't want to put it for all of the AI to learn from it for free. And talk to us. We'll be very happy to talk to you. Thank you so much.
Thank you.